Welcome everyone to today's video. It's going to be the first of two videos for talking a little bit more about ideal gases, kinetic theory of gases, as well as then starting to talk about real gases. Okay. So we talked about the ideal gas law and getting that from empirical observations, but we can also derive the ideal gas law from just basic physics and some calculus using also the Boltzmann distribution function, which won't go into too many details about this today, but will come up later in the semester in a little bit as well when in chemistry 3340. Okay, so let's start with a cube of length L, okay, where we have some gas particle in this cube. This gas particle is bouncing around at some velocity, right? That's velocity in the x, y, and z direction. And we'll just focus on the x direction, okay? Right, so after the molecule travels a distance 2L, it's going to hit both walls and return to its initial starting position, okay? Right, so it travels a distance of L, hits one wall, and gets back, and then travels a distance of L again, and hits the other wall and gets back, right? And it's going to be in its initial position and its same initial velocity, right? Because it went one way back and then it's going back the other way, right? So the time it takes for this to occur, right, is just that change over distance divided by the velocity in that direction, right? Well, that change of distance is 2L, and the velocity is just v of x, right? Whatever it is in the x direction, and that is the time it takes to traverse that distance for this molecule. Okay. So the average force that that box feels, okay, is related with the average momentum that the particle is exerting, or the momentum change, sorry, that the particle has, divided by the average time that that momentum is being exerted over, okay? Right? Because a force is related to a change in momentum, right? When you change momentum, it's due to some force being applied, okay? And so that's where that relationship between momentum and force come in, right? It's right? And so the momentum change, right, is 2 times the mass times the velocity in the x direction, right? Because it hit the wall and went back the other way, right? We're assuming these are pure elastic collisions, right? No forces, no intermolecular forces, things like that. So when it hit the wall and came back, it's moving in the x direction, but now in the opposite way, right? And so this thing has changed its momentum, right? This momentum is changed by 2 times its original momentum, as it's changed by 1 times the original momentum to sort of stop, and then another times its original momentum to go back. Okay, that change in time, right, that we calculated in the last slide is just that 2L divided by Vx. Plug all that in, okay, and the average force is just going to be related to the mass of the particle times its average velocity squared divided by the length, okay? And so to get the average pressure, that's just the average force over some area, right? Now, if you remember, right, the average force was related with right, average force was equal to mass times average velocity, the x direction squared, divided by L, okay? If I take the length of this box times the area of the box, right, that is going to give me the volume of the box. And so this average pressure is just mass times the average velocity squared divided by volume, okay? Right, the average velocities in all 3 directions, but average velocity squared in all 3 directions are going to be the same, and so the total average velocity squared is just 3 times that in x direction, okay? So the total pressure exerted on this box, okay, is just going to be related to the mass of the particle times the average velocity squared divided by 3 times the volume, okay? And so that's just using Newtonian mechanics, assuming inelastic collisions, okay? and assuming, infinitesimal size of this particle, right? But then the question is what is the average velocity squared? Okay, and this is where the Boltzmann distribution comes in. Okay, the Boltzmann distribution function is this mathematically is related to the relationship between kind of the energy of a particle and its probability of being at that energy, and it's given by this relationship here. Okay, if we use the fact that we're dealing with a gas and its only energy is 1/2 mv squared, plug this into the Boltzmann distribution function, you get this function down here, related with capital M here, the molecular weight, and R is the ideal gas constant, and so on and so forth. Okay. And you can use the Boltzmann distribution function to solve for the average velocity squared. Okay, you take the velocity squared, right? So this average velocity squared using the Boltzmann distribution function is just the integral of v squared times the Boltzmann distribution function, which is a function of v. Okay, and that's how we get this here. And this lovely looking integral actually simplifies down to this 3 kT divided by the mass. Okay, so a very simple solution. Okay, so we plug that in and we get now that the pressure of one molecule, the average pressure of one molecule is equal to kT divided by the volume. Okay, if we have a total of n molecules, right, that are all identical, right, in terms of their mass, right, then the total pressure, right, in that box is related with the total number of molecules times kT divided by volume. And if we just divide both sides by Avogadro's number, right, okay, then we're going to get the pressure is equal to the number of moles, right, N here, this is the number of moles, right, and then times Avogadro's number times K, which is actually just equal to the ideal gas constant R, right, which in this case is 0.08206 liters atmosphere per Kelvin mole, right? Our ideal gas constant is just related to K, the Boltzmann's constant, okay, times Avogadro's number, literally, okay? And that is our ideal gas law, right? PV equals nRT, right? And we derived this just from the Boltzmann distribution function and some simple kind of Newtonian mechanics in this problem. Okay. So now, kind of related with kind of talking about the Boltzmann distribution function and things for ideal gases, we can talk about a couple other little things, right, for gas that often we care about, especially when we care about chemical reactions that occur in the gas phase, right? If we're looking at reactions that occur in the gas phase, we're going to be interested in collision frequency. I'm given by this simple Z here, okay? This is the number of collisions made by a molecule divided by the time in which we're counting these collisions, okay? Right, so if I'm over 10 seconds, how many collisions occur over those 10 seconds, right? And it's the number of collisions divided by 10 seconds. That is the collision frequency, okay? This is related, it has this relationship here for an ideal gas, where sigma is the cross-section of the molecule. It's roughly the size, right? It's the interaction size of that molecule, okay? VREL is the relative velocity. You get that from the Boltzmann distribution function, and it has this relationship with Boltzmann constant, temperature, and then mu here is your reduced mass. Okay, and then this eta symbol, N here, essentially, right? This guy here, right? That for an ideal gas is just related with its concentration, number of moles over volume, which is also related to the pressure divided by kT. Okay, so Z here can also be written as sigma V relative times pressure over kT. Okay. Then I can also talk about for gas molecules, what is its mean free path? Okay. And the mean free path is essentially how far can this molecule travel in space before it collides with something, whether it be another molecule, the wall, doesn't matter. how far can this thing travel before it's going to have a collision? Okay, all right. And mean free path is kind of an average distance, right, of what that is, right? And that is just going to be related to the velocity of the particle divided by its collision frequency, right? The velocity of the particle, right, tells you how fast it's moving over time, right, how much distance it travels per time. The collision frequency, right, tells you, right, how often you have a collision, right? How many seconds does it take to have one collision, right? And so that's what those relationships are. So plugging in for the collision frequency and simplifying, you get that the mean free path here, lambda, is just related to Boltzmann's constant times temperature over this cross section divided by pressure, right? And we get that because this velocity here, this velocity is the relative velocity. So I could have mentioned last time, right? Often what we're referring to as relative velocity is if you had two particles, right, traveling A and B, right? Let's say they're both traveling in this direction, right? But A is traveling faster, okay? Right, the relative velocity is just what is the difference in the velocities between particle A and B, right? How fast are they moving relative to each other, okay? That's the relative velocity, right? That's what it's called, relative velocity. It's what is the relative velocity between these two particles? How fast are they moving relative to each other, right? Their total velocity might be different, but if they're both traveling in the same direction, at the same rate, right, they would never collide, right? Their relative velocity would be 0, okay? All right, and so that's it for this section, talking about ideal gases. And next, we're going to start talking some about real gases.